Hello, I'm Ruqi. I'm going to present our work of consistent ZoomOut for map synchronization. This is a joint work with Jing, Peter, and Max. Map synchronization is an important problem in shape analysis. In general, we assume to be given a set of 3D models and a map network G relating them. In this talk, we assume the initial maps are given in both directions. We also assume G to be connected, but it doesn't have to be dense or of any spatial topology. Here, we show some typical initial maps computed by blended intrinsic maps. Such maps can be noisy and inconsistent. The goal of map synchronization is then to refine these maps by leveraging the information contained in map network. With the consistent ZoomOut method I'm going to introduce, we can synchronize and improve the map quality. Here we show the refined maps of our method. We can see they are both more accurate and more consistent. The basic idea of map synchronization is to regularize the map network by enforcing cycle consistency. By that, we mean the composition of maps along any cycle in the network should equal to the identity map. This idea has been studied for a long time. The early approaches use consistency voting to determine the inconsistent maps, and then replace them by the composition of the consistent ones. A more recent trend explores the low-rank structure of a consistent map network. There's another line of work that utilizes the function map representation instead of pointwise maps. Our framework falls into this category, especially our work is inspired by a recent pairwise functional map refinement called ZoomOut, which I will introduce in a bit. So this is the talk plan. Let's start with functional maps. Now we have two shapes and map T from S2 to S1. Given T, we can transfer a real value function f on S1 to a function g on S2 while simply pull back T sub f. It is easy to verify that T sub f is equivalent to T, and it is a linear operator that maps functions from one shape to the other. In practice, we express T sub f with some function basis. One commonly used basis is the eigenbasis of the Laplace spectral operator. It can be seen as a generalization of Fourier basis from Euclidean domain to 3D surfaces. Now, given a pair of functions g, f, and g related by T sub f, and the eigenbasis on each of the shapes, we can approximately express them as coefficient vectors a and b. Since T sub f is linear, we can found a unique basis transformation matrix C with respect to this T sub f, such that beta equals to C times A always hold. We call this C the functional map from S1 to S2. The C is a matrix of dimension k. Usually, k ranges from 50 to 200 is sufficient for most applications. The main motivation of doing map synchronization with functional map is that it allows algebraic manipulations of maps such as inverse and composition, which is shown in this slide. On the other hand, we can also treat the Laplace spectral eigenbasis as a high-dimensional spectral embeddings of a shape. For instance, for any point P, we can collect the value of the eigenfunctions at this point and form a k-dimensional vector phi of P. From this point of view, the functional map C plays a role of aligning the spatial embeddings. We can convert pointwise maps to the functional maps and vice versa. The former is done by definition. Indeed, the same pointwise map can be encoded by functional maps of different dimensions. It all depends on the choice of size k. On the other hand, since functional map aligns the spectral embeddings of S1 and that of S2, we can recover the pointwise maps with nearest neighbor search in the embedded space. Finally, not all functional maps are induced by some pointwise map. In particular, we denote by P the set of all such functional maps. The structure of a functional map is informative. For instance, in the original paper, the authors proposed to refine a functional map by promoting its orthonormality. This idea is further extended recently. In this paper of last year, the authors proved that enforcing the orthonormality of functional maps at multi-scales leads to a stronger regularization. Here, K indicates the size of eigenbases used to encode the functional maps. Furthermore, they propose a simple algorithm to efficiently optimize this multi-scale energy with the constraint that function map arises from some pointwise map. In short, ZoomOut converts back and forth between the functional maps and the pointwise maps, while progressively increasing the dimension of the spectral basis for functional map representation. Here we can see refining functional map at a fixed dimension 100 is trapped at some suboptimal solution, while the multi-scale approach quickly converges to the optimal map. Though being surprisingly simple and effective, ZoomOut also has some limitations, especially it is potentially biased and cannot adapt to shape collections. To see that, let's apply ZoomOut on the example we have seen in the beginning. We can see that due to the large variability among the shapes and the noisy initial maps, ZoomOut fails to improve the maps. So, the core question of this talk is, can we incorporate the multi-scale map refinement idea to a more general map synchronization problem? Of course, the answer is positive. We call our solution Consistent ZoomOut. As an overview, we actually propose two algorithms. The first one is called Consistent ZoomOut, which incorporates the multi-scale refinement idea to map synchronization. However, like many other map synchronization methods, Consistent ZoomOut only promotes map consistency and says nothing about the map quality. Based on it, we further design Consistent ZoomOut ISO for synchronizing near-isometric shape collections. In this case, we provide theoretical guarantee on both map consistency and map quality. The cycle consistency in terms of functional maps is formulated in this paper from 2013. Here, gamma is the set of all cycles in the map network G, and I is the identity matrix. The authors propose to approximate the given functional maps Cij with some low-rank latent objects Yi and Yj. Such approximation naturally implies cycle consistency. In particular, the latent objects Yi can be obtained by solving this quadratic optimization problem. In this formulation, the functional maps are of a fixed dimension. As a nature extension, we propose a multi-scale version which takes into account of the cycle consistency at multi-dimensions indicated by K. To deal with the cycle consistency at a single scale, we utilize the limit shape formulation, which can be seen as a canonical version of the latent approach we introduced before. Now, given a set of shapes and a functional map network among them, we can construct a well-defined average shape or limit shape S0 with respect to the shape collection and map network. S0 is determined by a set of Ys, which can be seen as functional maps from S0 to each of the SIs. Therefore, the input functional maps are approximated by composition of the Ys. For example, C12 here is composed by Y2 and the inverse of Y1, which goes from S1 to S0 and then from S0 to S2. Coming back to our energy, with the help of limit shape, we can compute the consistent approximation of G at each scale K. With this approximation at hand, we drop the high-order consistency terms and consider the simplified energy, which only involves the consistency along the edges of G. Note that we still have the constraint that the functional maps should be induced by some pointwise map. To this end, we expand these energy terms. So here the red box suggests the functional maps arises from some pointwise map pi, and while the green box suggests they are related by this limit shape. In this way, the pointwise map and the Ys are coupled. We then apply a half-splitting technique and propose an iterative algorithm which is similar to ZoomOut refinement. In general, we start with a set of functional maps of dimension k, compute the limit shape Ys, and then convert to pointwise maps using these Ys, and finally convert to functional maps of a larger dimension. The procedure continues until k reaches some threshold. The key difference between the zoom out and consistent zoom out is how we update the pointwise map. In zoom out, we compare the spectral embedding of S2 and that of S1 but modified by functional map C12, and then apply nearest neighbor search among these spectral features. Obviously, in this procedure, no information about the other direction of functional map C21 is used, let alone the other maps in the shape collection. On the other hand, in consistent zoom out, we use the yi to modify the spectral embeddings of Si and Sj at the same time to align with the limit shape basis, and recover the pointwise map by a nearest neighbor search between the new spectral embeddings psi I and psi j. Overall, our pointwise map conversion is less biased and leverages the information of the whole shape collection carried by the zoom out by the limit shape. To give some intuition, we consider a spectral shape collection that contains only two shapes. We have some patch-based initial map, which maps a patch of the target shape to one point on the source shape. In zoom out, the refinement is done directly with eigenbases. Due to the geometry variability, the bases of two L-planes can be more and more different when you increase the size of bases. In other words, it will be more and more difficult to align the two spectral embeddings by functional maps. On the other hand, with the limit shape formulation, we can extract the consistent part of the two sets of bases and modify the bases in a canonical way. In the end, we will have the new basis as shown in the bottom. As you can imagine, the pointwise map conversion is easier and more accurate in this way since they are already well aligned. As a result, the output of our method is more accurate and smoother than the output of zoom out. Here is another example showing the result of refining a pair of hands using zoom out and consistent zoom out. Again, our results are smoother and more accurate than that of zoom out. In the following, we consider a special case where we know the shapes of interest are near-isometric to each other, for example, a collection of human shapes. So now our goal is to recover the consistent isometry among the shape collection. To achieve such, we add the zoom out energy with respect to each functional map in the network to our multi-scale consistency energy defined before. Most importantly, in theory, we prove that the global optimizer of this energy recovers the consistent isometry among the shape collection. Again, we propose an algorithm to approximately optimize this new energy. The only difference between the two versions is that in consistent zoom out ISO, we apply a projection in the beginning such that all the functional maps equal to the transpose of their inverse. It is easy to verify that with this projection, the energy of zoom out vanishes if and only if the functional maps are consistent. So we come back to the previous situation. So here are a few implementation details. First, for simplicity, in each iteration, we only update the maps existing in the initialization, so the topology of the map network G is unchanged. That being said, our method can always output the dense pairwise maps in the end if needed. Secondly, we incorporate the consistency voting scheme into our framework to dynamically adjust the weight of the maps at each iteration, and it helps improve the results. The most time-consuming part of our pipeline is converting functional maps to pointwise map. To this end, we use the same subsampling trick from the ZoomOut paper and only compute the full pointwise map in the output stage. So now our code demo is available online. You can try it out. Now we show some experimental results. In the first set of results, we consider 3 datasets of human shapes, Skip, Faust, and a more recent Shake 19. In particular, we use the dense initial maps network for Skip and sparse ones for the rest. We compare our method to 3 kinds of baselines: the pairwise map refinement, map synchronization, and map synchronization with pairwise post-processing. Since human shapes are near-isometric to each other, thus the quality of initialization is not bad in general. So the pairwise map refinement such as ZoomOut and BCACP already produce quite decent results. On the other hand, by leveraging the information contained in the shape collection, we can do even better. Such improvement is not all about the gain of using shape collection. For example, we outperform the map synchronization baselines by a large margin, even when they are post-processed by the state-of-the-art pairwise map refinement method. Finally, we can also see that our algorithm designed for near-isometric shape collection works better in this case than the one only take consistency into account. In the second set of experiments, we consider the Shrek 07 dataset, where the shapes are more heterogeneous. In this case, we compare our method with the map synchronization baselines. These figures shows the accurate accumulative error curves evaluated on the given sparse landmarks within each class of the shapes. As shown in the figures and the numbers, the improvement of method upon the baselines with respect to the accuracy are clear. I would like to highlight that since the error are evaluated on sparse landmarks, it cannot fully reflect the quality of the maps. In this figure, we have some qualitative comparison of the maps among the cups. Obviously, our results are smoother and more consistent than that of the baselines. Our method not only improves accuracy, but also boosts the consistency of the refined maps. Here we pick two shapes from the Shrek 19 dataset. Then we compute the pointwise map T12 and T21 using different methods. Ideally, their composition should be identity maps. In this figure, we show the composed maps with respect to different methods. We can see that qualitatively, our results are close to the ground truth and are comparable to the results of PMF, BCICP, and RHM. It's worth noting that these methods are specifically designed to enforce the bijectivity of the pointwise maps, which is usually quite expensive and slow. On the other hand, our approach is efficient and encourages the consistency in an implicit way. Lastly, our results obviously outperforms the map synchronization baselines by a large margin. In this figure, we evaluate the consistency for the Shrek 07 dataset. We collect all pairs of maps from the map network and measure how close their composition are to identity maps. Again, our method returns significantly more consistent maps than the baselines. In this figure, we randomly stacked cycles of varying lengths among 20 hand models and visualize the composition of the maps along the cycles. We can see that our result is pretty stable with respect to the increase of the cycle length, while the baselines can only hold for small case. So, to conclude, we propose a simple yet efficient map synchronization method. Our method significantly improved both accuracy and especially consistency of the maps of interest. The key ingredient of our formulation is how we leverage the powerful multi-scale regularization. Finally, our method still suffers a few limitations. For instance, it depends on the quality of the initial maps, and all the theoretical results we reported in our paper are for full shapes. In the future, we plan to further improve the scalability of our method while some hierarchy design. And we are also interested in exploring how it works for other shape representations, such as point clouds or images. Okay, so this is the end of the talk. Thank you for your attention.